Okay, so now let's do a couple of examples related to power. So let's say that, for example, you have a couple of resistors connected in series. For example, you have, let's say that you have basically, let me get my electronics up here. Okay. Let's see. So let's say that you have a couple of resistors. For example, you have R1, R2, R3, and R4 over here, and these resistors are connected to a power supply, negative, positive, for example, this way. And this is a 6 volt, 6.0 volt power supply. This is R1, this is R2, this is R3, this is R4. And then you have here, this is a 10 ohm resistor, this is a 20 ohm resistor, this is a 50 ohm resistor, and this is a 100 ohm resistor, right? Now you have this combination of resistors and so you want to calculate what is the whole power dissipated by the whole combination. So you want to answer the question, what is the total power? What is the total power dissipation? What is the total power dissipation by the whole basically combination? And by combination I mean the combination of resistors. So we said that basically in the previous video, we said that it doesn't really matter whether you have a series combination of resistors or parallel combination of resistors. Basically the power dissipation, the total power dissipation in the circuit is always equal to the power dissipated by each of the resistors, which means that you can also essentially calculate the total resistance in the circuit, and from that you can calculate the power dissipated in one single resistor, meaning that you have 10 plus 20 plus 50 is equal to 80. That's 180 ohm R of T of this circuit. The total resistance is 180 ohms, right? So 180 ohms, we said that basically P is equal to either VI or P is equal to V squared to R, or you can say that P is equal to I squared times R. Now if basically you can imagine that if you have 180 ohm resistor connected to a 6 volt power supply like this, and that's a 180 ohm resistor, and that's a 6.0 volt power supply, then the power dissipated by this resistor would be V squared to R. So V over here is the supply voltage. So you have basically square this voltage divided by the resistance, meaning that you would get basically 36 divided by 180, which is equal to 0.2 watts. So P would be 0.2 watts. Of course, you would get 0.20 watts, actually 0.20 watts, because basically that would be the same thing as 1 to 5, 36 to that's 36 two basically significant figures take this as, for example, 2 significant figures, that would be divided by this, so this should be 2 significant figures, and therefore you would get basically, if you simplify this, you'll get 1 to 5, which is the same thing as 0.20, for example, 2 significant figures, and then you can write that as also basically 2.0 into 10 raised to the power, for example, into 10 raised to the power into 10 raised to the power negative 1, which is 0.20 basically watts, right? If you care about the number of significant figures and things like that. Now, so the answer over here is basically, which is basically 0.2 watts, which is 200 milliwatt, right? In electronics, of course, usually people don't care about scientific notation that much. People usually talk in terms of, for example, when you get 0.20 watts, they call it, for example, 200 milliwatts. And so there is always ambiguity there. And well, that's the way that electronics usually works, unless you're doing something a little bit more scientific, in which case you really basically specify these numbers in terms of significant figure and so on and so forth. So that would be 200 milliwatts. Question number 8. That's 200 milliwatts, right? And what you can do, or what you could have done in the case of this circuit, so we know that basically P of total is equal to 200 milliwatts, right? Now, what you could have done as well is that you could have actually written the total power dissipation as P of T as equal to basically P, you know, that is equal to I squared times R, for example, right? So if I say that R of T in this circuit is equal to 180 ohms, as we calculated before, then the current going through this circuit would be basically I is equal to V to R, which is equal to 6 divided by 180 ohms. This is in volts, this is in basically in ohms, which is the same thing as 6 divided by 180 is 6 divided by 180 is equal to 1831, so 3, that's 30, 1 to 30 is the same thing as 6 divided by 180 is equal to 0.0333, so I take it as 0.033 amps, which is equal to basically 33 milliamps. 33 milliamps. So I in the circuit is 33 milliamps. Now 33 milliamps is going through the circuit, meaning that going through all of these resistors, through each of these resistors, actually not necessarily all of them, but through each of these resistors, a current of 33 milliamps is basically flowing. Now the power dissipation by this resistor would be basically the total power dissipation in the circuit would be P of R1 plus P of R2 plus P of R3 plus P of R4. P of R1 is basically I squared times R1. So I squared is basically 33 into 10 raised to the power, for example, negative 3, right? 33 into 10 raised to the power negative 3 raised to the second power times R, which is basically times 10, plus again the same current going through the circuit. Again, you can write it as 33 times 10 raised to the power negative 3 raised to the second power times basically times R2, which is 20. And as you can see, you can take this out, meaning that's the second power. You can take this out, you can write it as 33 into 10 raised to the power negative 3 whole raised to the second power times basically 10 plus 20 plus 50 plus 100 plus 100, and all of these are in ohm, right? And this is current in amps, so that would be amp squared, right? So that's the same thing as 180. That's the same thing as 33 into 10 raised to the power negative 3 raised to the whole raised to the second power times 180 in ohms, which is the same thing as basically 33 squared is equal to 33 squared is equal to basically 1089 into 10 raised to the power negative 6 into 180, and 1089 times 180 is equal to 196,020 into 10 raised to the power negative 6, which is the same thing as basically 0.196020 watts. And as you can see, this is the same thing as basically 0.20 watts. Is the same thing as 0.20 watts, which is the same thing as 200 milliwatts. And that is exactly what we got over here, 200 milliwatts. So that's basically how you calculate the power in this circuit. So that was question number the problem related to some problem related to power. Now again, in the same circuit, if you want to, for example, calculate the power dissipated in R4, it's very simple. You can basically calculate what is the power dissipation in basically in R4, for example. So if you want to calculate that, you can use the same relationship. And so the current going through the circuit is 33 milliamps, I squared times R. So P of R4 would be equal to I squared, which is 33 into 10 raised to the power negative 3 amps, whole squared times R, which is equal to 100 ohm, right? Which is equal to 100 ohm. And that is, what was that? 33 squared is equal to 1089 into 1089 into 10 raised to the power negative 6 into 100 in basically in amps squared. And basically then you have times 100 ohm, that would be the same thing as basically 1089 two zeros times 10 raised to the power negative 6 ohm times amp squared is equal to watt, and so you have 0.108900 watts, and basically round to two significant figures, you get 0.11, for example, watts, right? So that's basically, for example, how you calculate the power dissipation for R4, which is the same thing as, for example, 110 milliwatts. 110 milliwatts, if I'm not mistaken. Or you can call it 0.11 watt. Question number 9. B. Okay. Now another problem related to power in parallel resistors is that, let's say that, for example, you have 3 resistors in parallel. You have 3 resistors in parallel as follows. So suppose that you have basically a resistor over here, and a resistor over here, and a resistor over here. And so these are all connected in parallel, connected to a power supply. This is, for example, positive. And let's call this, for example, R1, R2, R3. R1, R2, and R3. And let's say that R1 is equal to, for example, 470 ohm, and R2 is equal to, for example, 2.2 kilo ohm, and R3 is equal to 3.3 kilo ohm, right? And your power supply is 15 volts. 15 volts. Now about this circuit, so you want to calculate the total power dissipation. You want to calculate the total power dissipation by the whole basically combination. So if you want to calculate that, of course what you can do is that you can calculate the power dissipation by this resistor R1, the power dissipation by R2, the power dissipation by R3, and then algebraically add them together. That you can do, because as we discussed before, like basically resistors in series, when you have resistors in parallel, the total power dissipation in the circuit is equal to the sum of the individual power dissipations is equal to the sum of the individual power dissipation in each of the resistors, right? So so you can do that, or you can calculate the total basically resistance in this circuit, which is of course not an easy task to do, but you can always use that basically no, we don't have it anymore. But you can always use that basically parallel resistor calculator that I showed you before. Of course, there must be some way to use this I mean, you could essentially use a calculator as well to do this, meaning that or you could probably write some program, for example, using, for example, C++ or something, and then put it on your computer whenever you want to do simple things like that. You can just enter the resistors into that program, and then it will give you basically the value. But well, this program is over here, and of course not all the time is it working properly. I'm going to use my calculator. So suppose that you have basically 1 over 470 ohm plus 1 over 2200 ohm plus 1 over basically 3300 ohm. That's the same thing as basically this number divided by this number. Now I have to take the reciprocal of this, which is 62040, and divide that by 179. That gives me 346 take 3 significant figures, for example. You would get basically 346 ohm, for example. Call it 360 ohm, 346 ohm, 346 ohm. So R of T in this circuit is 346 ohm. And it makes sense because you have about 3 kilo ohm resistor here, 2 kilo ohm resistor here, about 500 ohm resistor here. So the resistance has to be somewhere between these resistors, not more than that and not less than this one. So somewhere between the three values. So now what that means is that if your R of T is equal to this, and then you could imagine that you have a resistor over here with the value 346 ohm, and this is connected to a power supply like this. The power supply is 15 volts, and so the power dissipation in this resistor would be V squared to R, which is equal to 15 squared divided by 346, which is the same thing as 15 squared is equal to 625, I suppose. 225, I'm sorry, 225. Divide that by 346 is 0.65. Take 2 significant figures, 0.5 watts. 0.65 watts, which is equal to 650 milliwatts. 650 milliwatt is basically 10, right, that's 650 milliwatts. And if you're interested to basically calculate the power dissipation another way, so let me write this down over here. So P of T in this circuit was basically 650 milliwatts, right? Now another way that you can do the same thing is that if you basically calculate the power dissipation here times the power dissipation here times the power dissipation here, meaning that you can say that P of T is equal to, so if you use the formula V squared by R, you can write V squared by, or you can write basically P of T is equal to P of, for example, R1 plus P of R2 plus P of R3. Algebra is always your friend if you know how to use it, of course. I mean, sometimes it gets a little bit complicated, but most of the time algebra is a very good tool. So P of R1, we can write it as V squared divided by R1 plus V squared divided by R2 plus V squared divided by R3. And then you can write this as basically V squared times basically 1 by R1 plus 1 by R2 plus 1 by R3. And as you can see, exactly this way, we calculate the resistance of the total resistance in the circuit, meaning that we say that actually that is oh, well, that would be of course the reciprocal of the total resistance, but essentially you can say that, and then you can write this as V squared times, for example, you can write here, take LCM of these R1, R2, R3, right? And then over here you can write R2, R3 plus, for example, R1, R3 plus, for example, R1, R2, and then write it this way. So then P of T in this circuit you would have this formula to use in order to calculate it, meaning that basically R1, R2, R3, so you can say that, for example, then P of T is equal to V squared, which is basically 15 squared is equal to 225 times basically R2, R3 is basically in ohms, 2.23.3, 2.2 into 10 raised to the power 3 into 3.3 into 10 raised to the power 3 plus R1, R3, which is 470 into 10 into 3.3 into 10 raised to the power 3, and then R1, R2 is the same thing as basically 470 and 2.2, 470 and 2.2, so 470 times 2.2 into 10 raised to the power 3, divide that by basically 470 times 2.2 into 10 raised to the power 3 into 3.3 into 10 raised to the power 3, all in ohms, right? And then you can write this as, take a 10 raised to the power 3 out from the numerator here. You can write this as 225 times 10 raised to the power 3 times basically 2.2 times 3.3 times 10 raised to the power 3 plus 470 times 3.3 plus 470 times 2.2 divided by, take it 10 raised to the power 3 out from the denominator, you will get basically we don't really need to do that because they are already multiplied. So 470 times 2.2 into 10 raised to the power 3 into 3.3 into 10 raised to the power 3, and then you can cancel these two out, for example. And so now if you give this to a calculator, what you will get is basically 225 times basically 2.2 times 3.3 into 10 raised to the power 3 plus 470 times 3.3 plus 470 times 2.2, and divide that by 470 times 2.2 times 3.3 times 10 raised to the power 3, and close that and close that. You will get 0.65. You will get 0.65 watts, which agrees with 650 milliwatts that we got over here. It's got to 650 milliwatts. So that's how you calculate power in a circuit like this. Of course, there is all kinds of tools for this on the internet, and as mentioned before, you can always basically write simple programs in C, C++ to do these kinds of things for you. But essentially, before you use those programs, of course, you need to understand how these circuits actually work, right? Now, in the same circuit over here, so if you want to, for example, calculate the power dissipated by R1, for example, the power dissipated by R1. So how do you calculate that? So to calculate the power dissipated by R1 is basically this resistor here. So you can use basically P is equal to V squared to R, and write P of R1 is equal to basically 15 squared divided by 470. And that is basically in volts, that is in ohm. So that's the same thing as 225 divided by 470, which is equal to 0.478, so 0.48 watts, which is the same thing as 480 milliwatts. And that is 11B. Okay, that is also, for example, one thing that you can do in these circuits. That is that. Now let's do another question related to these DC circuits, and that is basically, suppose that let me read the question myself. Okay, so there is a circuit over here that you need to suppose that here you have a 24 volt supply, and each of these resistors is 33 ohm. And so you want to calculate this I1 over here. So you have this I1 going through this resistor, I2 going through these two resistors, and this is I going through the whole circuit. So to calculate I1, essentially you need to basically, it's a very simple circuit, meaning that since you can think of this circuit as essentially a resistor over here in parallel with another resistor over here, and they are connected to a power supply, right? So that the current going through this branch has nothing to do with the current going through this branch. This branch has its own current, this branch has its own current, and they have nothing to do with one another whatsoever, except that if I call this I1, and if I call this I2, and if I call this, for example, I, then of course I would be equal to I1 plus I2. But I1 is not going to influence I2, nor is I2 going to influence I1 in any way. They are completely independent, right? Which means that basically you need to, if you want to calculate your I1 over here, you have a 33 ohm resistor here, and you can just simply apply the Ohm's law to this resistor. There is a 24 volt supply on the two ends of the resistor, which means that V is equal to IR, 24 volts is equal to I, which is equal to what you want to calculate, times R, which is equal to 33 ohm. So I is equal to 24 volt divided by 33 ohm, which is the same thing as 24 divided by 33 is the same thing as 24 divided by 33 is the same thing as 0.72, for example, 0.72 amps, which is the same thing as 720 milliamps, right? 720 or 700, you could call it 730, of course, because you have to round it to two significant, 730 milliamps, and that's basically the answer there. It's in B. So that's basically this question. Now let's do another one of these, and these are essentially basically the Kirchhoff's voltage and current laws that that you can use in DC circuits. Now suppose that you have a circuit something like this. There is a so now suppose that you have some circuit like this. I calculated these things over here, but then there was a slight problem here, so I will write this again. So basically what we have here is basically two resistors over here, and this resistor is also connected here, and then there is another resistor here, there is another resistor here, there is another resistor here, and let's call this, for example, let's call this I1, for example, I2 in this direction, and let's call this, for example, I3, let's call this I4, and let's call this I5. These are in the other direction, meaning that relative to this node, let's call it Z, for example, relative to this node, I1 and I2 are coming in, and I3, I4, and I5 are going out of the node. Now you know that based on the Kirchhoff's current law, all basically the algebraic sum of all the currents coming into a node is supposed to be equal to the algebraic sum of all of the currents leaving that node, meaning that all of the currents coming in have to be accounted for, and they all have to leave that node. Nothing can remain there, or nothing can be unaccounted for as far as current is concerned. Now let's suppose that basically let each of these resistors have a value of, for example, 820 ohms, right? Now suppose that each of these resistors over here on the top, they lead to a light bulb of the exact same wattage, meaning that, for example, you have a light bulb over here, and that light bulb is connected to this node, and this is connected to ground. Another light bulb over here connected to this node, and again the other end connected to ground, and there is a light bulb over here connected to this node and connected to ground, and these light bulbs have the exact same wattage, meaning that if basically the three light bulbs having the exact same wattages, that means that they draw the exact same currents from your power supply, right? Because as long as V is constant, then current is going to be the same, meaning that P is equal to VI. If your P is basically, if P is supposed to remain the same, if P is supposed to remain the same, meaning that if the wattages of these light bulbs are exactly the same, then assuming that the voltages on these light bulbs are the same, then the currents going through them are going to be the same, meaning that meaning that the current leaving this node is going to basically, whatever the amount of current here is that is leaving this node is going to be basically divided equally through these 3 resistors and leave the node, basically, right? Because basically, again, the wattages of these 3 light bulbs are exactly the same, right? And let's say that basically, let's assume that basically I1, this current over here, is 50 milliamp. And let's assume that I2 is equal to 70 milliamp. Okay. Now, what is the power dissipated in the resistor carrying current I5? So in this resistor, call it, for example, R4, for example, this resistor over here, call it R4. What is the power dissipated in this resistor, meaning that what is P of R4? So basically, you know that based on the Kirchhoff's current law, all of the current coming in has to go out, meaning that 50 milliamp plus 70 milliamp is coming in, which is 120 milliamp coming in, and therefore 120 milliamp must go out. Now, we said that since these light bulbs have the exact same wattages, that the 120 milliamps going out is going to be divided exactly equally between the 3 branches, which means that each of the branches gets 120 milliamp divided by 3, which is equal to 40 milliamp, right? So that means that the current going through this resistor is 40 milliamp, meaning that I of R4 is equal to 40 milliamp. And the value of R4 is 820 ohms, which means that P of R4 is equal to I squared times R, which is basically 40 milliamp. The current going through the resistor is 40 milliamp, 40 into 10 raised to the power negative 3, raised to the second power times 820, which is the value of the resistor, which is the same thing as 1600 into 10 raised to the power negative 6 times 820, which is the same thing as basically 1600 times 820 is 1682, and you have 3 zeros there, and so you have 6 times 2 is equal to 12, 1, 48, 49, 0, 82, and you have 2, 11, 1, 12, 13, 0, 0, 0, and then multiply that by 10 raised to the power negative 6, you'll get 1.312. Take that as 1.3, so that's equal to 1.3 watts. That means that the power dissipated in this resistor is going to be 1.3 watts, and that's basically how you would, for example, calculate basically the power dissipation, for example, in this resistor. The important thing in this circuit is that all of the current coming into a node, all of the current coming into a node basically must go out into different nodes, and no current can be unaccounted for. Okay, so now the next question that we have is another question. Let me read the question myself first. Okay, so now let's say that you have this circuit over here. You have a power supply, and this power supply is connected to a resistor over here. Let's call that, for example, R2, and then another resistor, let's call that R1. Another resistor over here we have, let's call it R3 and R4. R3 and R4. R3 and R4. The power supply here is E, and that's basically the circuit that you have. Now suppose that these resistors are basically R1, R2, R3, and R4 are in the ratio 1 to 2 to 4 to 8. So you can say that R1 to basically R2 to R3 to R4 is equal to basically 1 to 2 to 4 to 8. To 4 to 8. And let's say that your supply voltage is 30 volts. Okay. Now what is the voltage E2 here, or the V of R2 basically? What is the voltage of V of R2? Right? V of R2. So in order to calculate this voltage, so basically you do not know the value of R1 or R2 or R3 or R4. You do not know the value of them. But you can use this ratio essentially in order to calculate basically some typical resistance for the circuit. Meaning that you can essentially, what you can do is that you can actually basically add all of these together, all of these numbers, which is, of course, these are ratios, not the value of resistance here. Meaning that, for example, when you say that, suppose that you have a circuit over here, you have two resistors over here and connected to a power supply. If I say that, for example, this is R1 and this is R2, and R1 to, for example, R2 is equal to 3 to 4, you cannot, of course, you can imagine that, or you can assume that, for example, R1 is equal to 3 ohm, and relative to R1, then R2 would be 4 ohm. That would not be incorrect. That would be correct. But then as long as the ratio of R1 to R2 remains 3 to 4, whatever value you choose for R1 and R2, that would be okay in that circuit. Meaning that, for example, suppose that I take R1 as, for example, 75 ohm. Then R2 has to be basically 100 ohm. And 75 divided by 100 is actually equal to 3/4, right? Because divide by 25, you'll get 3, divide by 25, you'll get 4, 3/4. Or you can basically, in the same way, you can say that, for example, I take R1 as, for example, 300 ohms, and then R2 has to be basically 400 ohms. 400 ohms. And that would also be correct, meaning that R1 to R2 is equal to 300 ohm divided by 400 ohm, which is equal to basically 3 to 4. The ratio remains the same. So these are ratios. Now, when you have these ratios, in order to calculate, sometimes you have to calculate, for example, something in your circuit, and the only information that you have is ratios. In that sort of situation, what you do, and that would be the simplest way to deal with that situation, is that you basically take these two numbers that you get for the ratio, 3 and 4, and you just simply add them together. 3 plus 4 is equal to 7. That means that basically the sum of these two numbers becomes 7. And so the sum of these numbers becomes 7. Or, well, this would get, I mean, this would get into algebra. Let's not do that. So basically what I mean to say is that or in this particular case, for example, now what you need to do, let me be more concrete here. So let me be more concrete and practical here. So in this particular case, you want to calculate the voltage drop across R2, right? So to calculate the voltage drop across R2, you have to apply Ohm's law to R2, or you essentially have to write V of R2 is equal to basically R2 to R of T times V of S. V of S being E here, basically the power supply. So so then you really don't need to well, all that you need to do is that you need to know the value of R2 and the value of total resistance in the circuit, right? And you don't have it over here. So I can take some typical values for the values of these resistors, meaning that I can say that, okay, so since these resistors are in the ratio 1 to 2 to 4 to 8, so what I can do is that I'm going to say that let's say that R1 is equal to 1 ohm, which is the simplest way of dealing with this problem, taking it as just simply 1 ohm. You don't have to then multiply it by any number. And then relative to that, of course, then R2 has to be equal to 2 ohm. And then relative to that, R3 has to be equal to 4 ohm. And then relative to that, R4 has to be equal to 8 ohm. And that is basically, that gives you some values for these resistors, right? Now, you have now the value of R2, you already have it over here, and the R of T in this circuit would therefore be 1 ohm plus 2 ohm plus 4 ohm plus 8 ohm, which is equal to 12 plus 6 is equal to 15 ohm, right? So then you can say that V of R2 is equal to basically 2 to 15, both in ohm, times basically 30 volts. And these two will be cancelled out. 30 divided by 15 is equal to 2. That would be 4 volts, right? So that means that the voltage drop across R2, across this resistor, therefore would be 4 volts. So V of R2 is equal to 4 volts. Now, you can actually do an experiment here, meaning that having the same ratio, I'm going to solve this problem in a different way. Meaning that since I know that basically this ratio must exist between the value of the resistors that I have in the circuit, so I'm going to say that, for example, now R1 has, for example, a value of 3 ohm. So relative to that, R2 must be 2 times that, so 2 times 3 is equal to 6 ohm. R3 must be basically 4 times that, 4 times 3 is equal to 12 ohm. And R4 is basically 8 times that, 8 times 3 is equal to 24 ohm, right? That's the meaning of ratio, meaning that the ratio has to remain the ratio. You cannot disturb the ratio. That has to remain the same. And if that's the case, then the circuit is going to behave as it should. And so now the value of R2 becomes 6 ohm. In the previous case, the value of R2 was only 2 ohm, right? But then now what happens is that the total resistance in the circuit also changes with that, meaning that R of T is equal to 3 ohm plus 6 ohm plus 12 ohm plus 24 ohm, which is equal to basically 9 plus, and that is 36. 9 plus 36 is 45 ohm, right? R of T is equal to 45 ohm. And now you can say that V of R2 is equal to R2, which is equal to 6 ohm by 45 ohm times V of S, which is basically 30 volts, and these two you can cancel out. Divide by 15, you get 3, divide by 15, you get 2, and that's 12 divided by 3, which is equal to 4 volts, the same voltage, right? You got the exact same voltage, although the value of R2 has changed, and the value of R of T has changed as well, but the ratio has remained the same, meaning that then the voltage, of course, will not change. So that's the meaning of ratio. So the V of R2 was therefore 4 volts. That was question number 15. Right. Okay. Now I'm going to end this video here, and we will continue with a couple more questions of the same type in the next video. Thank you.